you catch that the first time around, you're never gonna catch it. Procedures.
We're gonna back from what, 2-3 years ago.
I teach you to say that in
Alright.
Spanish class.
Everybody's got their calculators out? Have your calculators out? So that we can talk about all this stuff as we're going along and you can learn how to punch the numbers in. If you don't have your calculator here, then make sure you take really good notes about how to punch these things in. Okay? Alright. The mole.
Oh, mole's fun. Mole's a good.
The mole in chemistry is a little bit different than the mole in biology. The mole in biology could be the furry little animal with the squinty eyes that digs tunnels underground. A mole in biology could be the precancerous skin lesion, right? A mole in chemistry is a different kind of thing altogether. A mole in chemistry is a quantity. Now, we talk about the quantity of a dozen. A dozen equals how many pieces? 12 pieces, all right? If we say it's a baker's dozen, then it's 13 pieces. If you have a gross of something, does anybody know how much a gross is? It's a dozen dozens, it's 144 pieces, all right? So these are all words that we use to represent a numerical quantity of something. In chemistry, we use the mole, and the quantity of a mole is this enormous number, 6.02 times 10 to the 23rd pieces of anything. So let's talk about how many that is. It's a whole lot of stuff. Those of you that had lab on Monday, my favorite joke is, if as a teacher for 35 years, I would be willing to take my entire 35 years salary as a mole of pennies. You go, wow, she's cheap. You know, teachers were all pretty economical, right? But she's really cheap. Well, no, if I had a mole of pennies, and say I'm going to live another 25 or 30 years, I could spend $1 million a day until I die. Then, if I died in 25 years, I have 2 sons, each of them who would inherit what's ever left, each of them could spend $1 million a day for the rest of their lives, and there would still be money left over for my grandchildren. So there's a lot of pieces in a mole. You have to take this decimal and you move it 23 places to the right with 21 zeros after it. And that's because we're talking about itty-bitty, tiny things like atoms and molecules. So when you're making conversions, say for example I had 357 eggs. Okay? We're just going to use these as an example. I have 357 eggs. Could you tell me, by looking at that number, how many dozens there are?
Yeah.
Well, not by looking at that number, you can't. Not just by looking at it. You'd have to use a conversion factor. And the conversion factor is 1 dozen is 12 pieces, or 12 pieces is in 1 dozen. And both of these are equivalencies that can be used in similar ways. So we could say we have 357 pieces, and we'll call them eggs, right? We want to know how many dozens we have. We're going to use a conversion factor that gets us from pieces to dozens. Now, I know most of you probably could just do that in your mind. You say, oh, I want to know how many dozens I have. I know that number. I'm just going to divide by 12, right? Most of you can do that in your brain. However, I'm going to encourage you to do it in the manner that I'm going to show you now, because the first few calculations we're going to do are what we call one-step conversions, and they're very simple. And you can probably do them in your brain. But if you do them according to the method that I'm showing you, when they get to be more complex and they have multi-step conversions, then your life is going to go a lot easier when you can't just do it in your brain. So please follow my advice. All right, dozens to pieces. Which one is bigger, a dozen or a piece? A dozen. So you put the one in front of the thing that's bigger. In 1 dozen, how many pieces are there? 12 pieces. All right, so then I simply would take in my calculator now, and I want to do this with real numbers before we get to these itty-bitty numbers, and I'm going to input the number 357. Now, what mathematical function am I going to use here? Am I going to multiply or am I going to divide? I'm going to divide. I'm going to say 357 divided by 12, and what number do I come up with? 29 point, what's my change then? We'll say 29.8, so it's approximately 29.8. And what were my units here? Dozens. Okay, I have that many dozens. So I have almost 30 dozen eggs. So if I said, all right, I'm making these whopping huge omelets, and these whopping huge omelets are 12 eggs per omelet, how many omelets can I make? 29, maybe 30 if I kind of cheat a little bit on that last omelet. Right, yes, human error. There we go. All right, we could do it the other way. If I said I had 130 dozens, and I want to know how many eggs that is, I can do the same thing in reverse. I can go from dozens, right, on the bottom, to eggs or pieces on the top, and 1 to 12 is the ratio still. And now on my calculator, I would punch in 130. Am I going to multiply or divide by 12? I'm going to multiply by 12. And what number do we come up with when we take 130 times? How much? 1,560. I got a whole lot of eggs that I can make some omelets with using that idea. All right, well, let's try that now with this idea of a mole. All right, keeping in mind that 1 mole is 6.02 times 10 to the 23rd pieces, and those pieces can be atoms, molecules, bunny rabbits, pennies, marshmallows, whatever you want to call them. But you need to make sure that you put the units, okay, whether they're atoms or molecules, and also put the substance, whatever it is that we're talking about. I'll show you what I mean. So for example, I said I've got 2.5 moles of carbon atoms. I have 2.5 moles of carbon atoms. And I want to know how many atoms of carbon is that in 2.5 moles. Well, you all can probably just do that in your head, right? 6.02 times 10 to the 23rd times 2.5. But let's do it using the conversion factor, and this is called dimensional analysis, which once again I'm going to encourage you to use. Even though they're very simple right now, these problems, they get much more complex. So that many moles of carbon, and I want to go from, and now these are my units, and I'm going to tell you every single number that you write down in the next couple of lessons, which involve stoichiometry. I want you to make sure you have units and substance on every single number. That will cut down your errors by 90%, right? 90% or better is an A. If we all do that, everybody gets A's, right? And I would be the best chemistry teacher on campus. So make sure you put units and substance for everything. So now I'm going to take those units and substance, I'm going to put them on the bottom of my conversion factor, because those are the things that I want to cancel out, moles of carbon. I want to know how many atoms, basically that's a piece at this point that I'm looking at. So I want to look at atoms of carbon on the top of my conversion factor. Now what's bigger, a mole or an atom? A mole. So we're going to put 1 in front of moles. How many atoms is in a mole? Okay, we're going to put Avogadro's number, 6.02 times 10 to the 23rd atoms. And now I want you to take out your calculators, and I want you to look for these buttons. It's either an EE button if it's a scientific calculator, and it's often a second function. If you have a scientific calculator, if you have a regular old calculator, sometimes it is a button that says EXP, and some of the newer regular calculators, I've seen ones that look like this, times 10 to the something. Okay, you don't want to use this button. That is not the button you want. Do not use 10 to the x. So you need to find this button as a second function, EXP as your button, or if you have one of the newer calculators that's not a scientific calculator, it might say something like this, like times 10 to the something. Has everybody located that button on their calculator? Okay, if you have not, raise your hand and let me come around, take a look at your calculator. Maybe your neighbors can help you also. If it's a scientific calculator.
So you have to section.
That she said we had to memorize. I'm scared just because I have my lab right now.
Alright, is everybody located their EE or their EXP button? Alright, so now what you're going to do is this. Now please follow the key sequence that I tell you to do. Don't try and jump ahead. I'm going to borrow your calculator. Okay, so now here's the key sequence that we're going to use for this calculation. Alright, we're going to take our 2.5, so I'm going to clear my calculator. 2.5, so put in 2.5 first. Everybody do that. Don't step ahead of me. Make sure you stay with me. Now we're going to push in times. So go ahead and push in the multiply. Now we're only going to put the first part of Avogadro's number, the 6.02. Please don't go past 6.02. So we're going to punch in 6.02 and then stop there. You do not push in the times 10. This portion of that number is put in when you push either that button, or that button. So you do not push in times 10. What you do is this. Now, if you have a scientific calculator, please don't do any button pushing until you watch what I'm doing up here. If you have a scientific calculator, it's usually a second function. On this calculator, it's a second function, and the EE button is right there. Let me get this down a little bit further so you can see the calculator. Second function EE. So what I did was I punched in 2.5 times 6.02. Then I'm going to push second function EE, which substitutes for times 10. And now you'll see on my calculator, hopefully the display reads here, it shows on the calculator,
One single E.
it shows, hopefully, you can't see that very good.
Yeah.
Oh, the
that
brain in the
white-
calculator.
that white button on the side of that.
Well, your button should have, it should say 2.5 times 6.02.
Pressing second. And then do that. There we go.
Ooh, thank you, Larry. You're the man. You're the man. All right, so that's what it should look like. And then you just punch in 23, because that's the exponent, and then enter. Now, what your calculator is telling you at this point is this. 1.505 e to the 24 means this. So this is what your calculator is telling you. You need to know how to read this, because that's not what the answer is going to look like on the exam. The answer on the exam is going to look like this. It's going to say 1.505 times 10 to the 24th. That's what your calculator is telling you when it says that. It actually means this number right there. All right? That's what it means. Now, if you punched in those values in your calculator and you didn't get 1.505 e to the 24th or some version thereof, if it's to the 23rd or the 25th, you are doing it incorrectly. And you will do it incorrectly on the exam. And believe me, the publishers of the exams know what students do incorrectly, and they will put that as one of the choices on the exam. So make sure that you know how to punch the buttons in. Now, if we thought about sig figs on this, remember sig figs are based on our original information in the problem, which was here. How many sig figs are in 2.5? 2. Now, we don't take any conversion factors into account for sig figs, because that's not something we measure directly. That's a variable and a value that we pulled in from outside. It was not measured. So that doesn't count for sig figs. It's only the original information in the problem. So how would I report my final answer here? 1.5 times 10 to the 24th. Now I've got to have some units and substance here. What are my units and substance? Atoms of carbon. All right, so that gets you from moles to atoms of carbon. Now we're going to go in the reverse direction. Say, for example, I'm going to use a different substance. Say I had 360 million water molecules. That's a whole lot of water molecules. All right. I want to know how many moles of water are there. It's like I have 360 million eggs. How many dozen eggs do I have? Right? You could do that probably in your head, but let's do it with dimensional analysis. So 360 million is what we're starting with. And what are my units and substance here? Molecules of water. So my units and substance on every single numerical value. Times, now I want to take the units and substance, I'm going to put them on the bottom of the conversion factor here. Molecules of water on the bottom, right? And now what am I going to? Moles of water. So moles is my unit, substance is still water. Now what's bigger, a mole or a molecule? A mole. How many molecules is in a mole?
6.02.
Avogadro's number, so 6.02 times 10 to the 23rd. Now, let's practice doing that in our calculator. Larry, I'm going to steal your calculator again, if that's all right.
No, it's not okay.
Oh, darn, too bad. All right, we're going to put this in. If I was going to put this in scientific notation, how would this number change if I was going to put it into scientific notation? 3.6, second function exponent. What would be my exponent? 3, 6, 7, 8? to the 8th. Now am I going to multiply or divide by Avogadro's number here? Divided by 6.02, bless you, 6.02, second function exponent, 23, and then enter. So what would I report this answer as? Keeping in mind, how many sig figs do I have in my original numerical value there?
2.
Only 2. Very good. I'm glad to see you guys are getting this sig fig thing. All right, so what should I report my answer as?
6.0.
Very good. 6.0. Then what do I report as the rest of the answer? Times 10 to the negative 16. So do I even have a mole?
No.
I don't even have a mole in 360 million. A mole is a whole huge number. I have much less. Now, what are my units in substance here? Mole of H2O. All right? All right, we are beginning our stoichiometry journey, and I'm going to show you a portion, the first part of what we call the stoichiometry flowchart that corresponds to this. We know how to go from moles of something to the number of pieces of that stuff, that same stuff. So right now, the portion of our stoichiometry flowchart is this right here. We're going to add a piece. We're going to go from mass of that thing to moles of that thing. Okay? So now before we can go from mass of that thing to moles of that thing, we have to have a definition of what we call the molar mass. Now we discussed this a little bit in lab this week, so those of you on Monday may remember this definition. The molar mass is the mass, and I'm going to put it in grams, of 1 mole of any substance. And it turns out the periodic table is super duper helpful in trying to figure this stuff out. The periodic table tells us how much a mole of anything weighs based on its average molar mass. So if you look on the periodic table, we look at any of these things. Can I count out a mole of atoms? If I counted out and I sat down and I had a handful of carbon and I had a little itty bitty tweezer that was big enough to pick out a single carbon atom at a time, could I count out a mole?
No.
Well, not in my lifetime I couldn't. I'd have to turn that over to my sons and my grandchildren to actually do that counting, right? After they inherit the millions of dollars that I would from my mole of pennies from my salary. No, you couldn't do that. But what you can do is you can use a balance, right? We could go into the lab. Could you weigh out 12 grams of carbon? If I gave you a pile of carbon, could you weigh out 12 grams of it? You could, 12.01 grams. That's exactly the mass of 1 mole of carbon. Pretty amazing. Oxygen. How much would you have to weigh out a mole of oxygen? 16 grams. Copper, one of my favorites. How much would you have to weigh out a mole of copper atoms? 63.55 grams. Pretty amazing that you can go from something you can't see, you can't count, to something that you can measure. All right? So in order to do that, we use this idea of molar mass, and we can do some calculations, like what's the molar mass of water? Well, if you look at the molar mass of water, we just have to add up the individual components. Hydrogen is 1 gram per mole, but there's 2 of them there, so we have 2 hydrogens times 1.0 grams per mole, and this is the unit of molar mass. Okay, grams per mole is the unit of molar mass. So I have 2 hydrogen atoms in there. Each mole of hydrogen weighs 1 gram per mole. So 2, that gives me 2 grams due to the hydrogen. Water, I have 1 oxygen. If I look, and I round these to tenths generally. If I look at oxygen, rounded to tenths, it's about 16 grams per mole. So 16 grams per mole gives me 16 grams due to the oxygen. I weigh all that, or I add all that up together. the molar mass of water is about 18 grams per mole. So, since water is about 1 gram per 1 milliliter, if you poured out 18 milliliters of water, you have about a mole of water molecules. That's about a pretty big slug of water, right? You take a big drink, you're drinking about a mole of water. So next time you take a big drink of water, think about that. I'm swallowing about Avogadro's number of water molecules here. It'd be amazing how good things you think about chemistry. Let's do one that's a little more complex. Let's do the molar mass of something like lead nitrate, right? All right, if we look at lead on the periodic table, where the heck is lead? PB. There it is, 207.2. So I got 1 PB times 207.2 grams per mole is 207.2 due to the lead. Now we have to think about nitrogen. How many nitrogens do I have in a unit of lead nitrate? 2. That's important. So nomenclature comes back again. 2 nitrogens. Each nitrogen, based on the periodic table, weighs about 14.0 grams per mole. So 14.0 grams per mole is going to be about 28 grams due to the nitrogen. Now finally, here's the hard one. Here's oxygen. How many oxygens are there in a unit of lead nitrate? 6. 3 times 2 is 6. So we got 6 oxygens. Each of them, we're going to round it to 16 grams per mole each. So 16 times 6 is 96 due to the oxygen. Then we just add them all up. $331.2 grams per mole. So what that means now is if I have 1 mole of lead nitrate, it weighs 331.2 grams. If I have 331.2 grams of my, I always put units in substance, lead nitrate, I'm going to have 1 mole of it. So these are both equivalencies that work. And you can flip them either way. And as long as you know how to calculate the molar mass of any substance, you can go from how many moles you have to mass, and you can go into the lab and actually weigh it out. So let's look at where that goes in our stoichiometry flowchart. Remember, we had moles of our substance, and we know that we can go to number of pieces using Avogadro's number. 6.02 times 10 to the 23rd is what gets us back and forth between number of pieces and moles of A. Now we're going to go from mass in grams to moles of A. And the thing that gets us from mass in grams to moles of A is molar mass. And the molar mass you get from the periodic table. Bless you. So let's try some calculations. Let's say I need, for an experiment, I need 3.2 moles of water for a particular experiment. And I need to know how much water I need to either weigh out or pour into a graduated cylinder, right? So I want to go from moles of water to mass of water. So there's the connection I'm making, which is molar mass. So I'm going to go moles of water. Where's that going to go? Since I'm using dimensional analysis here. On the bottom of my conversion factor, moles of water. And I'm going from moles of water to mass of water. So what units in substance should I put on the top? Grams of water. All right, if you put units in substance on every single conversion factor before you plug numbers in, you'll also reduce your errors by 90%. So please make sure you do that. All right, whenever you're going from moles to anything else, mole 1 always goes in front of moles. In a mole of water, how much does that weigh? 18 grams. We just figured that out. Now, on my calculator, am I going to multiply or am I going to divide 3.2 by 18? I'm going to multiply. So what is 3.2 times 18? Somebody with me. 57.6. And what are my units in substance here?
50.
Grams of H2O, which is also 57.6 milliliters, right? Of H2O. And that only works for water.
Yeah, she's figures.
I do. Thank you, Larry. Thank you. So we need to change that to what? 58 grams of water. Excellent. All right, let's try another one. We'll keep our mole conversion up here. Now I want to go from, say for example, I want to go from mass. I've got 4.7 grams of, we'll use our lead nitrate since we already know the molar mass of our lead nitrate. We don't have to redo that. And now I want to know how many molecules of lead nitrate are there. All right, so now it gets a little more difficult. Problem gets a little more difficult. There's my stoichiometry flow chart. So now where am I starting on my stoichiometry flow chart? Mass. I'm starting up here. Is there a direct route to go from mass to number of pieces? No. What I have to do is I have to go from mass to moles first, and then from moles to number of pieces. So that's going to require 2 conversion factors. So we're going to start with our 4.7 grams of lead nitrate. And I'm going to set up 2 conversion factors. And like I said, they start to get a little bit more difficult, so it's better to use my method. And now units in substance is going to go on the bottom of my first conversion factor. What am I going to put on the bottom over here? Grams of what? Of lead nitrate. PbNO3(2). So now I'm going from grams of lead nitrate on my flow chart here to moles. So what are the units in substance I'm going to put on the top of my conversion factor? Moles of what? Lead nitrate. Important to make sure you put, because we're going to change substances a little bit later next week, so make sure you put all that up. Okay, I'm not going to put any numbers in yet. Let's put all the conversion factors, all the units in the substance before we plug numbers in, and I promise that will eliminate a whole lot of your errors. So now on the bottom of the second conversion factor, what units in substance do I want to put so that they cancel? Moles of what? Of lead nitrate. Do y'all see why I'm doing that? Right? Because moles of lead nitrate's up here, and I want to put it down there to cancel. If I'm looking at my stoichiometry flow chart, the first step got me from mass to moles. Now I'm at moles, I want to go to number of pieces, so I'm at the second conversion factor. So what units in substance am I going to put on the top? Molecules of? Very good. All right, now we're going to go back in and put the numbers. After you put units in substance for everything and figure out where you're going to go, then you put the numbers. Moles to anything else, what's the coefficient that always goes in front of moles? 1. Over here we do the same thing. Moles to something else, boom. Just put the 1 right in front. That'll keep you straight. In a mole of lead nitrate, how do I figure out how much it weighs?
We have to do each.
We just did that.
Just did that, so we got that up here. It's 331.2 grams, so we're just going to put that number in. Right? That's how much a mole of that junk weighs. And now a mole of lead nitrate is going to have how many molecules in it? Avogadro's number. Let's double check that our units in substance cancel. Grams of lead nitrate to grams of lead nitrate, right? That cancels. Moles of lead nitrate to moles of lead nitrate, that cancels. So the units that fall out are molecules of lead nitrate. Now with my calculator, I'm going to punch in the numbers. All right, so first we're going to punch in 4.7. And I'm going to multiply or divide by that 331. Divided by 331.2. Now push enter in between each of the calculations. Don't keep it going as a running, because different calculators handle this type of thing differently. So it's always best to push enter in between each one. Now am I going to multiply or divide by Avogadro's number? Right, times 6.02, second function EE23, enter, and what number do you guys get? 8.54, but that's not the whole number. What am I going to report? 8.54 times 10 to the 21st. What are my units in substance here? Molecules of lead nitrate. And yeah, we got to look at sig figs too. How many sig figs should I use? Just 2, because that one only had 2. So 8.5, I would say 8.5. All right, how are we feeling so far? This is the hardest stuff you will do in this class. If you can get through this stuff, the rest of chemistry is going to be a piece of cake. All right? Let's do some more. Since we're all pretty happy now, let's do some more. Yes? Well, it gets harder than this. It gets harder than this, but this is on the road to the hardest stuff. Next week will be the hardest week of the whole semester. How's that? All right, let's try another one. Let's try another one. Say, for example, I have...
When we're doing trying to find the molar mass, do we always round it to the 10th?
Yes. Molecules of potassium iodide. How many grams is there?
Instead of hydrogen being 1.01.
Okay, here we go. Here's another one. Starting out with 4.7 times 10 to the 51st molecules of potassium iodide, and I want to know how many grams I have in that 4.7 times 10 to the 51st molecules. So I'm going to start with my initial number, 4.7 times 10 to the 51st molecules of Ki. Now let's look at my stoichiometry flowchart. I'm going to fold the top of this page back. All right, so where am I starting on my stoichiometry flowchart here? I'm starting here with number of pieces. Is there a direct route to go to mass? No, so I got to go to moles first, then to mass, right? So I need how many conversion factors? 1, 2. All right. Now, units in substance on the bottom of my first conversion factor is going to be molecules of potassium iodide. All right, so I'm here, and I want to go to moles. So what are the units in substance I'm going to put on the top of my first conversion factor? Moles of Ki, right? Now I'm going to take moles of Ki, and what am I going to do with those units in substance? I got to put them where? On the bottom, moles of Ki. And I'm right here right now, and where do I want to go? To grams. So grams of what? Ki. All right. Now we go back and put the numbers in. Moles of anything to molecules. What's the number in front of moles? Moles to grams, the number in front of moles is? How many molecules are in a mole? Avogadro's number. How do we figure out how many grams of Ki we got in a mole? Got to add them up. So let's look at potassium. Potassium is 39.1. So 39.1 for the K. Iodine is 126.9 for the I. So 166 grams per mole, looks like, if I did my math right. All right, now with my calculator, I'm going to punch in my first number, in this case, 4.7, second function, exponent 51. Am I going to multiply or divide by Avogadro's number? Divided by 6.02, second function, exponent 23. And I always push enter in between because different calculators handle this type of thing differently. So it's always a safe bet to just push enter. Now am I going to multiply or divide by 166? Times 166, enter. And it looks like my calculator says 1.296. I will look at sig figs in a minute. Times 10 to the 30th. And what are my units in substance here? Grams of Ki. All right, now how do I got to fix that sig fig there? 1.3. All right, you guys are on your way. You can now do the entirety of homework 11. Woo. Yes?
Are we going to have any numbers that are bigger than can fit in my calculator?
I hope not. I hope not. Only geologists deal with numbers like that. We're talking about 60 gazillion years, right? Or our national deficit. Which you guys, by the way, are gonna have to pay, not me. I'm gonna be withdrawing from the system. Y'all are gonna have to pay for it. Like billions of dollars? That's insane.
Looking forward to it.
Vote. Go out and vote.
I'm looking for dual citizenship in Spain. So, there you go.
Yeah, my son lives in Canada now. I'm gonna go visit him over spring break. It'll be pretty sweet here.
So we snowbirds down here, right?
Yep.
My wife works at Banner Heart Hospital, so
Yep.
we get guys that are they would rather pay for a evac to back to Canada than to get treatment done in America. I'm brutally honest, and because the way that the laws are written in
Put that incorrectly.
Canada,
That one's multiplied. Oh no, you did multiply over here. Yeah, multiply that here. Yeah. And then I got 76.
Pay out of pocket for
4.7.
go.